Let's run through details about Earth system models. We already mentioned them a little bit in the last chapter. Here we'll go into some gory details and uncertainties and how they are used for making projections and what uncertainties we have to worry about in the projections and so on, and what is the future direction that will be needed for Earth systems, not only as a tool to understand the changes in the Earth system, but also to provide information at various timescales which keep emerging because the decision making is not as simple as one would imagine. What is the use of projecting out to 2100, for example? Is there a shorter time scale at which decisions are better served by the Earth system model outputs and so on? Okay, so this is just an overview, and we'll look at the various flavors which I already mentioned in terms of complexities and details. Their development, including some evaluations, benchmarking, and touch on some optimization, which basically means there are parameters in the models which are based on empirical evidences from data, and they have to be constrained by some way or the other. This we looked at in some other form before, looking at details of the description and number of processes included as a measure. We will look at the details as we go along, and the number of interactive components of the climate system included in the model. So on the lower end of the simplified models, we have zero-dimensional energy budget models. So basically the whole Earth, let's say, is just one unit. Some energy is coming in and some energy is going out. There are no dimensions, and then there are one-dimensional energy budget models which can include, for example, just energy diffusion in some box which has various components being balanced. Energy budget basically always takes the incoming shortwave, outgoing long wave, and has to make assumptions about how the equator to pole temperature gradient is, for example, being served by the energy budget. So there are various details. We won't need them here because we will not really be using them to understand the Earth system, even though they have been used in the past for some process understanding. Earth system models of intermediate complexity we have talked about. There are two-dimensional EMICs, as they're called, and three-dimensional EMICs. So they often are used for making what we call transient runs, which we mentioned before. So instead of looking at just last glacial maximum or the Paleocene-Eocene thermal maximum scenarios with the forcing of the time, continental configurations of the time, and so on, you actually make a long run starting at some point, initialized somehow, and capture the variability along the way. So it can be a different solution based on how much information gets accumulated that matters, let's say going from now to the last glacial maximum, or starting from the last interglacial during the Eemian 130,000 years ago forward to the last glacial maximum, or from the last glacial maximum into the Holocene, and so on. General circulation models is a more generic term that evolved to represent atmospheric general circulation models, ocean general circulation models, atmosphere-ocean general circulation models. Every time you say atmospheric general circulation model, it has some representation of land, and the ocean is usually prescribed as just sea surface temperatures. There are also simpler versions of ocean with just a slab ocean and so on, in which case you need additional details about how to represent ocean energy transport, etc. Again, just for your information. And we have the Earth system models, which vary in complexity and details by a lot. So it's not a very unique definition, but we have looked at the Brotherton diagram already, which we will look at again and see how that itself has to evolve for meeting the requirements of decision makers and policy makers for global change considerations for decisions and policies. We looked at this before from this BAMS paper, which talks about how to organize Earth system models for producing stakeholder needs, as it is usually referred to. So not just putting up model output on a website and hoping somebody will use it, but actually have some sense of what decision makers and policy makers are looking for, and produce usable information and not just what is considered useful by the modelers. Okay, so here again we consider the phase space of spatial resolution, which depends on whether you are trying to resolve tornadoes or hurricanes or global climate or regional climate. Temporal resolution depends on whether you're trying to capture year to year, seasonal to seasonal, or decade to decade variability, or longer. Simulated time scale is, we will see that when models simulate the 20th century, they are initialized somehow, let's say, with the industrial revolution time period, atmospheric composition, and some sort of an ocean initial condition, and then you integrate forward with adding anthropogenic forcing, volcanoes, solar variability, and so on. So those would be called simulated timescales. Replicates, so what are you trying to actually capture? Uncertainty assessments. Dynamic coupling is basically between ocean and atmosphere, land and atmosphere, land and ocean, and so on. And the processes you want to resolve, whether it's El Nino, monsoon, responses to aerosol loading, and so on, and the number of processes. So here again, the energy budget models are shown in this bluish line. EMICs have a different phase space. Atmospheric ocean GCMs have a different phase space, and Earth system models occupy some part of the phase space. And this variable dynamic approach the authors propose means you can choose these parameters to see what is the best tool for your need. Okay. This is the Brotherton diagram we looked at, where we went from external forcing like solar variability, orbital forcing, and volcanoes, which are considered external forcing because they are taking out stuff that is deep within the earth and throw it into the atmosphere to perturb the climate, right? Usually it wouldn't come out. So anything that perturbs the radiative forcing we call external forcing. And human activities, of course, in terms of emissions, land use change, are now external forcings as well. Okay, so we had the atmospheric physics, dynamics, and tropospheric chemistry and biogeochemical cycles, and the various time scales of going to millions of years with ice cores and sediment cores and geological evidences, etc. And we talked about some feedbacks between moisture and other components of the water cycle. Okay, so this is just history in the Stefan et al. Paper, which looks at the evolution of the Earth system, looking at organizations involved, publications that are being critical, and campaigns and events that have worked towards defining the evolution of the Earth system. We have seen another version of this before, so I won't go into it, but we talked about Vernadsky's biogeosphere interactions back from 1926. There is also the Svante Arrhenius paper going back to 1896, Lovelock's Gaia hypothesis, Brotherton diagram, Brundtland report, which started to formulate the global warming problem, Schellenhuber's second Copernican revolution. It's a subjective choice. Vostok ice core records, international geosphere biosphere synthesis, and again subjective choices of certain papers. But we know that programs like the World Climate Research Program, IGBP, IPCC, International Human Dimensions Program, and a system science partnership of these things. And now everything has been clubbed into future Earth, but WCRP remains under the World Meteorological Organization along with World Weather Research Program, and they manage WCRP manages the IPCC process as well. So here are these campaigns and events. Obviously, we have looked at Keeling Curve a lot. There was the International Geophysical Year, NASA's Blue Marble, which changed the way we perceive Earth by looking at it from outside, gives us a sense of the human dimension causing so much perturbation despite the enormity of the planetary system, Earth system. Okay, the Anthropocene was proposed by Nobel laureate Paul Crutzen, which is now widely accepted. There are programs that were carried out in the Amazon, like the large-scale biosphere atmosphere interaction, and the Amsterdam conference, which defined the challenges of a changing Earth system. Okay, so that's kind of just a brief run through of where we are headed. We will keep adding details about what are the various problems that are requiring us to think of Earth as a system, and what are the components that go into it, what are the uncertainties associated with them, and so on. Okay. If you're not a modeler, it's a good reference set of podcasts. If you are a modeler, you probably already know most of the things that are being mentioned here, but this is providing a context for understanding the Earth system for adaptation and mitigation, or global change science for application. Okay, so hopefully useful for all.